Next thing to look at is combinations. So the difference with a combination as opposed to a permutation is the order is not important. So instead of an arrangement, it's just a selection of objects. How many ways can we select the objects? In fact, some people like to do permutations by working out the number of combinations first and then just arranging those objects. So they select, then arrange. I mean, it works, but a permutation does it all in one hit. So all right, this time we're not interested in the order. So how's it going to change? So we've got objects in a line. So as far as we're concerned, AB is the same as BA. It's the same selection. It's a different arrangement, but it's the same selection. We've got the same objects. Okay. So again, let's build it up. I think it's the easiest way to do. So if we've got 5 objects and I only want to arrange 2 of them. So for 5 objects, arrange 2 of them, there's all our permutations we could have. So there's 20 all up. But if I'm not concerned with the arrangement, it's simply the selection. Some of these are the same. So the AB is the same as the BA. So let's cross out all the doubling ups that we've got there and see what we've got left. And the number of combinations is the number of permutations, but I divide it by the number of ways those objects could have been arranged because I'm not concerned with the arrangements. So divided by 2 factorial, and sure enough I end up with 10. Well, just to confirm it, let's have a look at if we arrange 3 of them. If we arrange 3 of them, there's now 60 different permutations. But again, there's a lot of doubling up there. The ABC is the same as the BAC, as the CAB, and so on. So let's cross anything that appears more than once. We should be left with the number of permutations divided by the number of ways we could have arranged those 3 objects. So there should be just 10 left. 1, 2, 3, 4, 5, 6 in that column, 7, 8, 9, and 1 in that column. Yep, sure enough, we've ended up with 10. Okay. So basically, we're dividing out the number of ways we could arrange the objects. Well, if that's the case, then we can come up with a formula for that. So n different objects, we're going to arrange k of them, but not concerned about the order. I suppose another way of saying that is simply we're just going to select k objects. So the number of permutations divided by the number of ways we could arrange the objects. Now, if you remember the formula for npk, it was n factorial over n minus k factorial. So now that we're also dividing by k factorial, we get this formula, n factorial on n minus k factorial, k factorial. The 2 numbers on the bottom will always add to give the number on top with this. On your calculator, again, you have a button for that. This one's on the divided by key. You'll find it on the divided by key to save some time. But once again, we do need to know the formula for those situations where we're dealing with algebra rather than dealing with numbers. So, okay, here is a classic question, something a lot of people want to know every week. So how many ways can you select 6 numbers from 45? Well, there's 45 numbers. We're going to select 6 of them. We don't care about the order, so it's a combination. So there are 8,145,060 possibilities. Now, by the way, if you were going to play Lotto, it's 70 cents a game. So if you wanted to cover every possibility, it would cost you, there you go, about $5.7 million. So if you've got a spare $5.7 million lying around and you want to guarantee that you win Lotto, there you go. Of course, take you a while to fill out all the coupons, but it would guarantee it. However, there's still a gamble. There's another little rule. What you're hoping for is that no one else picks those numbers as well. Because when they do, you share the prize. So you don't want to be sharing the prize with anyone if you've spent that much money. Committees of 5 people. We're choosing from 7 men, 4 women. How many committees are possible? No restrictions. So no restrictions. That basically we're talking about, what did I say, 7 and 4, 11 people. So it'll be 11C5. From the 11 people, we're just going to select 5. And we don't care about the order, so it is a combination. So there's 462 different committees that we could have. What about if the committee contains only males, as used to happen many, many years ago now? They said, oh, can't have a woman in the committee. Goodness me, no. So let's just see what narrow-mindedness does. Because now we would only be selecting from 7. And there's only 21 possible committees now. So the diversity of the possible committees has shrunk dramatically. But then we got enlightened. We said, no. We want the committee to contain, well, at least one. We'll let one on to start off with and we'll see how we go. But here's where complementary events idea. Because if I said at least one woman, I've got to work out, well, what happens if there's 1 on the committee, or maybe there's 2 on the committee, or maybe there's 3 on the committee, or maybe there's 4 on the committee. So rather than doing that, we do the complementary event where we'll take away what we've already worked out, where there's none on the committee. So now we've got 441 possible committees. Okay. I think I know a few of you probably enjoy playing with cards now and then, playing particular games associated with them. I'm in no way promoting gambling here, of course. Hands of 5 cards. A lot of games do that, 5 cards. And there's 52 cards in a deck. How many possible hands are there that you could be dealt? Well, 52 cards, we're just going to select 5 of them. So what do we got there? 2,598,960 possible hands. Okay, what's the probability of getting 3 of a kind? For those who don't play cards, 3 of a kind just basically means you've got 3 cards with the same number or picture, if you like, on it. So what we're going to do here, we're going to look after the restriction first. Well, we want to know which one is going to be our 3 of a kind. Will we have 3 aces? Will we have 3 2s, 3 3s, 3 4s? So of the 13 different things we could have, I'm going to choose one of them. So 13C1. Now once I've chosen that, well, there's 4 of those in a pack, and we want to choose 3 of them. So 14C3. We now need to get another 2 cards to complete our hand. We've already dealt out 3 cards. So that leaves me with how many cards to choose from? 48, not 49. Okay, I was wondering if anyone was going to make the classic mistake and go, oh, 49. But of course, I don't want to choose. Say we decided we're going to get 3 aces. Then I don't want to choose the other ace. Well, actually, in reality, I'd love to choose the other ace because then I get 4 of a kind. But if I'm looking for 3 of a kind, I don't want to choose the other ace. So it can't be included in the other 2 cards that we're going to pull out. So there's only 48 cards I'm going to select from. And wouldn't it be lovely if those 2 cards were also of the same? Because then we'd have a full house. Again, not that I'm know anything about gambling or anything like that. Okay, 58,656 different possibilities there. Well, let's work out the logical question then. What's the probability that, well, there we are, we're playing a hand of poker, for just give it some random name. What's the probability of 3 of a kind? And we can see there we've got 58,656 over that 2 million, etc. Sometimes it's nicer just to look at it as a percentage because it gives us an idea of what's our chance of winning. So 94 on 2915, it simplifies down to, it's around about 3.2% chance of winning. And in fact, that's how they work out which hand beats which. It's all based on the probability of getting that particular hand. 2004 HSC, we've got a 4-person team and we're going to choose from 9 women, 7 men. So similar sort of thing as that committee question. How many ways can we choose the team? Well, there's 16 people all up. We're going to choose 4 people. So 1,820. Part 2 of that question was, well, what's the probability then that the team will consist of 4 women? So 14, well, now we're only choosing from the 9 women, so 9C4, 126, so our probability of a 4-women team, 126 on 1820. And that simplifies down, there we go, 9 in 130. So that's a typical sort of HSC question there. Okay, going to look at some other ideas that can help when solving these problems. So the first idea is dividing into groups. So if you're going to divide a group of m plus n objects into two groups, one group has m, one group has n, so you're splitting them up, then the total number of selections will be m plus ncm. Because all you're really saying is how many ways could I choose m objects from m plus n? You don't have to worry about the other group, because as soon as you've chosen the m objects, the n that are left over naturally become the other group. Okay? In factorial notation, of course, it's m plus n factorial and m factorial n factorial. But of course, if the groups are the same size, then it's a little bit different. So we're going to divide a group of two m objects into two groups, but both of these groups have m objects. We still go 2mcm, but we divide it by 2 factorial. And here's the reason why. 6 people. Going to divide them into two groups of 3. I could choose these 3 first, then they become the other group. But hang on a sec, I could choose these 3 people first, and then they become the other group. It's exactly the same selection. So when you have the same number in each group, you need to divide by the number of ways those groups could be arranged, because otherwise you'll end up double counting in that. So number of selections, 2 MCM, but it's over 2 factorial. So if we put it in factorial notation, we'd end up with 2m factorial and m factorial, 2 factorial. What happens now, we're going to divide it into 3 groups. So we've got m plus n plus p objects, but we're going to have into 2 groups, that should be into 3 groups, shouldn't it? Into 2 groups with m, n and p objects. That would be 3. Okay. Well, first of all, I'll just choose the group that has m objects. So I'll go m plus n plus p, cm. Now that'll leave me with n plus p objects. So from those objects, I will now choose n of them for the second group. And then I'll be left with p objects that will naturally become the third group. So what happens with all this factorial notation? So we'll have m plus n plus p factorial over m factorial n plus p factorial. But then it will be times n plus p factorial on n factorial p factorial. Look what ends up happening. It's simply m plus n plus p factorial, so the total number of people, but divided by however many are in the groups, factorial. So I don't need to do this chain of picking. I can just go, oh, well, I want a group of m, a group of n, and a group of p. So I'll divide by m factorial, n factorial, p factorial. So let's apply this idea. We've got 15 students. We're going to divide them into 3 equal groups. Equal groups. That will become 15 factorial over 5 factorial, 5 factorial, 5 factorial. Each group's going to have 5 people, but because they have the same number of people in them, I will need to also divide it by the number of ways those 3 groups could be arranged. Otherwise, I'll end up double counting groups. So we also have 3 factorial on the bottom of the fraction, giving me, oh, isn't that a lovely number? 126, 126. All right, we're going into a restaurant. The restaurant's got 3 tables. Each of those tables has 4 seats. 12 people arrive for the dinner. How many ways can they be assigned to the tables? 12 factorial on 4 factorial, 4 factorial, 4 factorial. But we'll also divide by 3 factorial, the number of ways we could arrange the groups, because they are of the same size. But in this case, I also multiply by 3 factorial. So in effect, I don't divide by the 3 factorial. I could have simply gone 12 factorial, 4 factorial, 4 factorial. What is the difference? The difference is, once I have selected the groups, I'm doing something with them. So back to our one here, having U3 on this table and U3 on this table is different to if U3 went on that table and U3 went on that table. If I was simply selecting 2 groups, I would divide by the 2 factorial in this case. But because I'm then going to place them somewhere, I'm going to say, well, you'll go on table A, you'll go on table B. That's different to if you went on table A and you went on table B. So in that case, we don't divide by the, 2 factorial, and in our example there, effectively, we don't divide by the 3 factorial. So we have 34,650. Okay? Right, so that's what I'm saying. If you're then going to arrange the groups, so you're sending them off to different tables, whatever it is, you might be picking 2 teams, and one's going to go on the left-hand side of the field, one goes on the right-hand side of the field, that sort of thing. Or one wears the blue jerseys, one wears the red jerseys. Then we don't divide by the number of arrangements. So a permutation is simply a combination multiplied by the number of ways the objects can be arranged. So that's what I was saying before, is some people like to think about it, I'm going to choose or select, then arrange. I'll work out the number of objects, then arrange them. The insertion method. This is useful when you've got this question where they say, oh, these people are not allowed to be together, or these objects are not allowed to be together. Okay? So we have the letter of the word sing. We're talking about things being between each other. Let's look at the word between. Arrange them in a line. How many ways can be arranged if all the E's are separated? So none of the E's can go next to each other. Okay. So traditionally the way we do it is we'd first of all go, well, how many ways can the E's be placed? You might do that by listing all the ways or something like this. And you go, well, hang on. I know there's 1, 2, 3, 4, 5, 6. There's 7 spots the E's can go. But the E's can't go next to each other. So I could place them like that. Or that last E could go on the second last one. Or the last E could go on the third last one. I'd be okay. Or I could do it like that, where I'll leave 2 between the first and the second E, and then the last E could go in the second last spot, or it could go in the last spot. So that's 2 ways. Or I could separate the first 2 by 3, and that leaves me with 1 possibility. Or E doesn't have to be in the first spot, so I could do it like that, but then that last E could move, so I've got 2 ways. Or I could separate the first 2, and I get that way. Now, is there any others? Yes, I could now move the first E along one, and I could go E, and then E, E. There's 1 way, giving us a total of 10 ways I could place the E's. So there's 10 ways I could place the E's. The rest of the question then becomes easy, because I just need to know how do I place the other letters, and I'll multiply it by 10. So 4 factorial for the other letters, 240. But that idea does require us to be very careful and make sure we get every possibility of how can we place E. What the insertion method is, see, normally we look after the restriction first, but with this one we say, no, I'm going to look at the unrestricted objects first. So there they are, B, T, W and N. I know there's 4 factorial ways that I can place those letters. And you'll notice I've left a gap. Those gaps are where the E's are going to go. 5 spaces have now been created. I can put the E's in any of those spaces. I just can't put 2 E's in the 1 space. But as long as I use those spaces, I'll satisfy the requirements of the question, because now I'm going to insert the E's between the other ones. Now in this case, order's not important, because the E's are all the same. So it will look exactly identical. So there are 5 spots for me to use, and I'm going to use 3 of them. I'm going to choose 3 of those to use. I come up with the same answer, 240. What about if exactly 2 of the E's are together? 2 of the E's are together. Well, again, I'll place the B, T, W and the N down. But now I'm saying there's 2 objects. There's one object that is E, and there's another object that's E. So now order's important, because they are different objects. So I will go, of those 5 spots, I'm going to use 2 of them, one to place the E, one to place the EE, and it's a permutation, not a combination. 480. All right, another idea. An idea called using separators. So if you've got a really large group and you're going to divide it up into smaller groups, that's when this idea comes in handy. We've got 3 pirates. Arr. They're sharing out the contents of a treasure chest. It's got 48 gold coins and 2 lead coins. The first pirate takes out coins one at a time. So the first pirate, go for your life, take out as much gold as you like. But as soon as you take out a lead coin, you have to stop. And then the next pirate gets to have a go. All right, you take out as many gold coins as you like, but as soon as you get a lead coin, you have to stop. And then the third pirate, you'll just get whatever's left. Okay. How many ways can those coins be distributed? What we do is we change the question into something else. So instead of coins, I'm going to think of letters. And so the lead coins are now L's, and the gold coins are now G's. And so the 2 L's, if you like, will be the separators for the 3 pirates. Wherever the L lands in this word I'm going to make that has 2 L's and 48 G's, that will determine how many gold coins each pirate will get. So the question then simply becomes, well, there's 50 factorial, because there's 50 letters or coins, and I'm going to divide it by 48 factorial for the 48 gold coins, 2 factorial for the 2 lead coins. 1,225 ways of doing it. That leads me to this, and you'll notice it says extension 2 question. How many ways can 10 identical coins be allocated to 4 different boxes? So you're going to put coins into a box this time. Well, I'm going to insert a separator. So I'm going to say the letter C represents the coins, the letter S is going to be the separator, and my question now is going to be, how many words can I make with 10 C's and 3 S's? Wherever the S falls, that would tell me how many coins I'm going to put in the box. So it becomes 13 factorial on 3 factorial, 10 factorial. So there's 286 ways of doing that. Now, as I say, that was an extension 2 level question. It's interesting that only 1% of the state got it right. That's the level of difficulty of that question. 1% of extension 2 students, so we're talking the very best students, got it right. But you know what's even more amazing? We then get to this one. Also an extension 2 question. A hostel has 4 vacant rooms. Each room can accommodate a maximum of 4 people. How many ways can 6 people be accommodated in the 4 rooms? Okay. Well, I know if there's no restriction, it'll be 4 to the power of 6. So the first person's going to come along and go, I want a particular room, has 4 choices. The second person's going to come along, 4 choices. The third person's going to come along, I've got 4 choices. So we'll end up with 4 times 4 times 4 times 4 to the power of 6. Okay. But I don't want there to be 6 people in a room. Okay. Because it says how many, see, maximum of 4 people. So I don't want all the possibilities with 6 in a room. Well, that would be 4C1. Because the first person would come along and choose the room, and everyone else, you've got to go in that room. So basically they're just choosing the room they're going in, 4C1. But we also don't want 5 in a room. So that would be 4C1, 6C5, 3C1. The logic there. We're going to choose which of the 4 rooms will have 5 people. Okay, we've worked out the room. Now we're going to choose which 5 people are going in that room. So 6C5. That leaves one poor person by themselves. They're going to choose from the 3 remaining rooms, 3C1. 72. That should cover every possibility now. So if I subtract, I get 4,020. Well, they did a bit better, 15%. Remember the last one, 1% got it right? Well, you'd think they did a bit better until I tell you one other piece of information. That was a multiple choice question. You would have thought if they just randomly guessed, 25% would get the right answer. So it's even less than just randomly guessing was the correct answer on that one. All right. Enjoy.